In the span of 9 days, the ground beneath one of the most densely populated coastlines on Earth moved 1,200 times. Not one earthquake, not 10. 1,200 individual seismic events, ranging from barely detectable microseismic pulses to tremors strong enough to rattle windows and send coastal residents out into the streets in the middle of the night. And here's the part that's keeping geophysicists at their monitors at 3 in the morning. This isn't random geological noise. This is a pattern. A specific, documentable, deeply concerning pattern that scientists who study megathrust systems recognize immediately because they've seen early versions of it before. The question isn't whether the Sunda Megathrust is under stress. It is. That's been established science for years. The question that 1,200 tremors in 9 days forces researchers to ask out loud, even when they're careful with their language, even when they're cautious about alarming the public, is whether that stress is finally approaching a threshold, whether the accumulated strain of decades, possibly centuries, of tectonic pressure is beginning to find a way to release. There are roughly 40 million people living within the direct impact zone of a major Sunda Megathrust rupture. 40 million. The coastlines of Sumatra, Java, and the surrounding islands represent some of the most vibrant, historically rich, economically vital communities in all of Southeast Asia. And right now, beneath those communities, beneath the fishing villages and the port cities and the resort beaches and the rice paddies, two of the most massive tectonic plates on Earth are locked together. And something is changing. This is what we know. This is what the data is showing. And this is why it matters. To understand why geologists are watching Indonesia right now with a level of attention that borders on alarm, you have to understand it. And what the Sunda Megathrust actually is. And why it dwarfs almost every other seismic threat on the planet in terms of sheer potential energy. Start with the geography. Indonesia sits at the convergence of multiple major tectonic plates, the Australian plate grinding northward and diving beneath the Eurasian plate along a subduction zone that stretches roughly 5,500 kilometers. That's longer than the entire continental United States from coast to coast. The fault system that runs along this boundary, the Sunda Megathrust, is not one single break in the Earth's crust. It's a network of interlocking fault segments, each capable of independent rupture, each storing decades or centuries of accumulated stress, and each capable of triggering its neighbors in what seismologists call cascading rupture. Now zoom in on population. The western coast of Sumatra alone is home to major cities like Padang, population approximately 1 million, sitting less than 20 kilometers from the trench axis. Banda Aceh, which carries its own devastating historical significance that we'll come back to, sits near the northern terminus of this system. Further south, Java's coastlines, among the most densely populated stretches of land anywhere on the planet, face direct exposure to any tsunami generated by a large rupture event. When researchers at the Earth Observatory of Singapore modeled the impact radius of a full or near-full Sunda Megathrust rupture, the numbers for population at risk climb past 40 million people almost immediately. Economically, this region represents an absolutely critical node in global trade. The Strait of Malacca, which sits in the broader influence zone of this fault system, handles an estimated 40% of global seaborne trade. That's trillions of dollars in goods annually. Oil from the Middle East moving east, manufactured products moving west, container ships threading through one of the narrowest and busiest maritime corridors on the planet. A catastrophic event here doesn't stay regional. The economic shockwaves travel. And what makes the current situation unprecedented isn't just the swarm activity. It's the location of that swarm activity, combined with GPS-based ground deformation data, combined with a 20-year post-2004 stress transfer cycle that geophysicists have been tracking with increasing concern. This isn't a random cluster of small earthquakes in a geologically quiet area. This is seismic unrest, concentrated in a zone that researchers have specifically identified as a seismic gap. A section of the megathrust that hasn't released significant energy in a documented historical period and is therefore considered, in the scientific community's careful language, to be significantly overdue. Compare this to other systems people might be more familiar with. The Cascadia subduction zone off the Pacific Northwest coast of North America generates enormous public attention and preparedness planning, and rightly so. But the Sunda Megathrust is longer, historically more active, and sits adjacent to population concentrations that dwarf those of Oregon and Washington. The 2011 Tohoku earthquake in Japan, The event that triggered the Fukushima nuclear disaster and killed nearly 20,000 people was a magnitude 9.0 event on a comparably sized subduction system. What scientists are now monitoring in Indonesia involves a fault system with the demonstrated capacity to exceed even that. A seismic swarm sounds almost benign when you first hear the term, like a weather event, something that passes. But what's happening beneath Sumatra right now is anything but routine, and understanding why requires a brief look at how stress actually moves through rock. Think of the tectonic plates as two enormous slabs of stone being pushed together by forces so immense they're almost incomprehensible. The Australian plate is moving northward at roughly 7 centimeters per year. That doesn't sound like much, but multiply that by decades, by centuries, and you accumulate an almost unthinkable amount of stored elastic energy, the geological equivalent of a spring being compressed, slowly, relentlessly, year after year. The fault doesn't move continuously. It locks. The rocks on either side of the fault boundary grip each other through friction, and while they're locked, the plates on either side keep moving, keep bending, keep storing energy that has nowhere to go. Until it does. A seismic swarm, particularly one concentrated along a locked fault segment, can indicate several things, and researchers are currently debating exactly which interpretation fits what's being recorded. One possibility is that the swarm represents relatively minor stress adjustment along peripheral fault structures, essentially the megathrust system redistributing pressure without triggering a major rupture. This is the more reassuring interpretation, and it has historical precedent. Swarms occur. They dissipate. The main fault stays locked. But here's where it gets genuinely concerning. The second interpretation, supported by a growing body of research from institutions including Caltech's Seismological Laboratory and the GFZ German Research Center for Geosciences, is that swarm activity concentrated in specific geometrical patterns along a megathrust system can represent what researchers call accelerating nucleation, the early phase of a major rupture process where stress is concentrating at a specific point on the fault, and small earthquakes are essentially cracking the rock around that stress concentration as the system moves toward a larger release. The 1/200 tremors recorded over 9 days, and this figure comes from BMKG's publicly accessible monitoring data, cross-referenced with the USGS Global Seismograph Network, are not uniformly distributed. They cluster. They show a spatial pattern that aligns with a specific segment of the Sunda Megathrust that last produced a major rupture in the early 19th century. That's more than 200 years of accumulated strain. Researchers at the Institut Teknologi Bandung, who study the GPS-based ground deformat ion data for Sumatra, have noted that coastal monitoring stations have shown anomalous displacement patterns in recent months. The land is moving in ways consistent with a locked fault that is beginning, in their words, to creep at the edges. Now, what would a magnitude 9.0 or greater event actually require in terms of fault geometry? Seismologists calculate earthquake magnitude based on the area of fault that ruptures and the amount of slip that occurs. A magnitude 9.0 requires roughly 500 kilometers of fault length and potentially 10 to 20 meters of slip. The Sunda Megathrust has segments, particularly the Mentawai segment off the west coast of Sumatra, that are long enough, locked enough, and stress-loaded enough to produce exactly that. Research published in the journal Nature Geoscience identified the Mentawai Gap as one of the highest-risk unruptured fault segments anywhere on Earth. That assessment was made years before this current swarm began. The SO2 monitoring data from satellite-based atmospheric sensors adds another layer of complexity. While elevated sulfur dioxide emissions are more commonly associated with volcanic activity, anomalous readings in proximity to active subduction zones can indicate fluid movement along fault systems, hydrothermal processes that reduce friction and potentially accelerate fault slip. The monitoring data from the past 60 days hasn't crossed alarming thresholds, but researchers at the USGS Volcano Hazards Program note that the baseline trends bear continued watching. What the current swarm represents, in the most honest scientific framing, is a system in motion. Whether that motion terminates in a swarm that fades or escalates toward a main shock cannot be predicted with certainty. But the magnitude of what hangs in the balance demands that we understand it fully. December 26, 2004. A date that reshaped how the entire scientific community thinks about megathrust systems, began with almost no warning. It was early morning, the day after Christmas, and the beaches of southern Thailand, Sri Lanka, and the Aceh province of Indonesia were full of tourists and local residents beginning a quiet holiday morning. At 7:58 a.m. local time, the northern segment of the Sunda Megathrust ruptured. The rupture propagated along approximately 1,200 kilometers of fault, moving at roughly 2.5 kilometers per second, and released energy equivalent to 23,000 Hiroshima bombs. The magnitude was ultimately calculated at 9.1 to 9.3, making it the third largest earthquake ever recorded on seismographic instruments. In Banda Aceh, the shaking lasted nearly 10 minutes. 10 minutes of continuous, violent ground motion that collapsed buildings, ruptured water mains, and left survivors too stunned to process what had happened before the next threat arrived. A local woman named Nurul, her account preserved in oral history documentation by Indonesian anthropologists, described looking toward the ocean after the shaking stopped and seeing the water pulling back from the beach in a way she'd never seen in her life. The fishermen around her, she said, ran toward the sea, thinking the receding water meant fish. Nobody had taught them what it actually meant. The tsunami arrived within 15 to 30 minutes in Aceh. Wave heights in some coastal locations exceeded 30 meters, roughly equivalent to a 10-story building. The total death toll from the 2004 Indian Ocean tsunami reached approximately 227,898 people across 14 countries. It remains the deadliest tsunami in recorded history. Now here's the crucial geological point, and it connects directly to what's happening right now. The 2004 rupture released enormous stress. But it didn't release all of it. The Sunda Megathrust is not a single segment. The 2004 event ruptured primarily the northern portion of the system. The Mentawai segment, the Enggano segment, and sections of the Java Trench system were not significantly involved in that rupture. In some cases, stress transfer from the 2004 event actually increased loading on those adjacent segments, a phenomenon called Coulomb stress transfer, where a rupture on one part of a fault system essentially squeezes stress onto neighboring locked portions. Research conducted in the years following 2004, particularly work by geophysicist Kerry C. and his team at the Earth Observatory of Singapore, helped reconstruct the Holocene rupture history of the Sunda Megathrust using coral. Microatolls, corals that grow to precisely sea level and therefore record vertical land motion with extraordinary precision over centuries. What that research revealed was alarming in its clarity. The Mentawai segment has historically ruptured in events comparable to or larger than 2004 on cycles ranging from 200 to 500 years. The last major rupture of that segment was in 1797 and 1833. Do that math. The 2004 event also produced a critically important scientific revelation. The monitoring systems in place at the time were completely inadequate. There was no functioning deep ocean tsunami buoy network in the Indian Ocean. There were no warning sirens on most of the affected coastlines. Emergency response plans either didn't exist or existed only on paper. The disaster exposed a monitoring infrastructure gap that the international community scrambled to address in the years that followed. BMKG's current network, the expanded DART buoy system in the Indian Ocean, the upgraded seismograph stations, all of it was built largely in response to 2004. The question that haunts researchers studying the current swarm activity is stark and uncomfortable. Are those systems, as improved as they are, sufficient for what might be coming? And are the communities in the potential impact zone actually better prepared than they were 20 years ago? Indonesia's Agency for Meteorology, Climatology, and Geophysics, BMKG, operates one of the most expansive seismic monitoring networks in Southeast Asia, and what that network has been recording over the past several weeks has prompted a significant internal reassessment of risk timelines. BMKG has publicly elevated its monitoring posture for the Western Sumatra seismic zone. This isn't a formal public warning, and that distinction matters because the agency is appropriately cautious about generating panic in high-density coastal areas where premature evacuation can itself cause casualties. But within the scientific community, the language coming from BMKG's technical briefings has shifted. Monitoring reports now describe the swarm as anomalous in duration and spatial distribution, which in the careful vocabulary of seismological institutions represents a meaningful escalation in concern. The DART buoy network, Deep ocean assessment and reporting of tsunamis now includes multiple operational buoys positioned in the Indian Ocean specifically to detect the pressure signatures of tsunami-generating seafloor displacement. These buoys feed data in near real time to warning centers in Hawaii, Australia, and Indonesia. The theoretical response time from a rupture event to a warning broadcast has been reduced from the catastrophic zero warning situation of 2004 to somewhere between 10 and 20 minutes for most affected coastlines. In places like Padang, where the city sits essentially on the shoreline with limited high ground immediately accessible, 10 to 20 minutes is not a comfortable margin. Here's a tension that disaster preparedness researchers openly discuss. The 20 years since 2004 have seen significant infrastructure investment, improved warning technology, and public education campaigns about tsunami. Evacuation. BMKG runs regular drills. Evacuation routes are marked. Vertical evacuation shelters, elevated concrete structures designed to be reached in minutes, have been constructed in some vulnerable communities. But coverage is uneven. Rural coastal communities, particularly on the outer islands closest to the trench axis, often lack both the infrastructure and the institutional connectivity to receive and act on warnings effectively. A 2023 assessment by the Asian Disaster Preparedness Center noted that while urban centers like Padang and Banda Aceh had made measurable preparedness improvements, overall regional readiness for a megathrust event remained significantly below the threshold required for acceptable casualty outcomes in a worst-case scenario. That report was written before this swarm began. The USGS real-time seismic monitoring data, publicly accessible through their Earthquake Hazards Program, shows the swarm pattern in aggregate. And what stands out to researchers examining that data isn't just the volume of events, but the depth distribution. A significant portion of the tremors are occurring at depths consistent with the plate interface itself, the actual contact zone between the Australian and Eurasian plates, rather than in the overlying crust. Interface seismicity, particularly in swarm patterns, is considered a more direct indicator of megathrust stress behavior than shallow crustal earthquakes. Scientists at the USGS Earthquake Hazards Program have not issued a formal elevated warning for this zone, but internal communications and published research briefs reflect active, heightened monitoring. Scientists and disaster modelers at institutions including Caltech, GFZ Potsdam, and the Earth Observatory of Singapore have run rupture scenarios for a full Sunda Megathrust release, and the numbers that come out of those models are, frankly, staggering. Though it's essential to understand them as modeling outputs, probabilistic scenarios, not predictions. In the event of a full rupture of the Mentawai segment producing a magnitude 9.0 to 9.3 earthquake, ground motion modeling suggests that shaking intensities across western Sumatra could reach modified Mercalli intensity levels of IX to X, described in that scale as violent to extreme. At those intensities, even earthquake-resistant construction suffers significant damage. Unreinforced masonry, the dominant building type in many coastal Indonesian communities, is essentially destroyed. The 2009 Padang earthquake, a magnitude 7.6 event on a subsidiary fault system, killed over 1,000 people and collapsed thousands of buildings. That was a fraction of the energy that a full megathrust rupture could release. The tsunami modeling is where the numbers become hardest to sit with. In a full Mentawai segment rupture scenario, models developed by researchers at Bandung Institute of Technology and validated against 2004 post-event surveys suggest initial wave heights along the nearest Sumatran coastlines could range from 10 to potentially 30 meters, arriving within 15 to 30 minutes of the rupture. In the transoceanic projection, those waves attenuate with distance but remain potentially damaging at the coastlines of India, Sri Lanka, Bangladesh, Myanmar, and Thailand, the same nations devastated in 2004. The modeling further suggests that wave arrival times in some of those more distant locations could range from 90 minutes to several hours, theoretically allowing for evacuation if warnings are issued and received promptly. The secondary effects in this scenario cascade outward in ways that extend far beyond the immediate earthquake and tsunami. Infrastructure damage to Indonesian ports, including the critical facilities at Belawan, Teluk Bayur, and Tanjung Priok, could interrupt supply chains across Southeast Asia for months. Submarine communication cables running through the region could be severed by undersea landslides triggered by the quake, disrupting internet infrastructure across a significant portion of Asia. Humanitarian response would face extraordinary challenges in accessing and supplying affected coastal communities, many of which become island-isolated when road and bridge infrastructure fails. The global economic modeling for a scenario of this magnitude, conducted by institutions including the World Bank and the Asian Development Bank in post-2004 risk assessments, projects potential losses in the range of hundreds of billions of dollars when direct damage, trade disruption, and humanitarian response costs are aggregated. And that's before accounting for the long-term displacement of coastal populations and the generational economic impact on communities that might effectively cease to exist in their current form. Could a smaller rupture occur instead? Absolutely. The fault system could produce a magnitude 7.5 or 8.0 event. Still catastrophic, still potentially tsunami generating, but far more geographically contained. It could also see a slow slip event, a gradual release of stress without a dramatic rupture that reduces the accumulated strain without a major seismic event at all. The scientific community is genuinely uncertain about which of these outcomes the current swarm activity is moving toward, and that uncertainty is honest, not evasive. The Earth does not issue press releases. What scientists can say, and what the monitoring data supports, is that the Sunda Megathrust system is not in a period of quiescence. It is active. It is stressed. And the swarm currently being recorded is occurring in a location and at depths that demand continued, intensive monitoring. Here's what matters most. Not the fear, not the worst-case number, but the awareness that comes from actually understanding what's happening beneath the surface of a region that the world too often only pays attention to after the disaster has already occurred. The Sunda Megathrust has ruptured before. It will rupture again. The geological certainty of that statement is about as close to absolute as earth science gets. What remains uncertain, genuinely, scientifically uncertain, is the timing, the magnitude, and the specific segment involved. Those are not evasions. They reflect the real limits of what seismological science can currently determine, and researchers are working actively, urgently, to narrow those limits. What found 200 tremors in 9 days tells us is that the system is not dormant. What the 200-year stress accumulation on the M9.0 segment tells us is that the energy available for release is enormous. What 2004 told us, in the most devastating possible terms, is that warnings and preparedness infrastructure are not optional. They are the difference between a disaster and a catastrophe. If you live in a coastal region adjacent to any subduction zone, and this includes the Pacific Northwest, Japan, Chile, New Zealand, and Indonesia, the most valuable thing you can do right now isn't to panic. It's to understand your local evacuation routes. It's to know how your regional warning systems work, what the sirens mean, and how much time you realistically have to reach high ground. It's to have that conversation with your family. The one that feels uncomfortable because nobody wants to imagine the scenario, before the scenario removes the option of conversation. Awareness is not the same as fear. Understanding a threat is not the same as being paralyzed by it. The communities along the Sumatran coastline that have integrated tsunami preparedness into daily life, where children learn evacuation routes the way children in other countries learn fire drills, represent a model that the rest of the high-risk world could learn from enormously. The ground beneath Indonesia has moved 1,200 times in 9 days. Scientists are watching, the monitoring systems are running, and now you're watching too. In our next video, we're turning attention to another fault system that's been generating its own alarming signals. The Hikurangi subduction zone off the coast of New Zealand, where slow slip events of unprecedented duration have researchers asking deeply uncomfortable questions about what comes after the slip stops. If the Sunda Megathrust is a spring being compressed, the Hikurangi system is a spring that's been quietly, invisibly releasing, and the implications of that are not what you'd expect. Subscribe if you want to stay ahead of what's actually happening beneath the surface of this planet. Drop a comment below. What questions do you have about the Sunda Megathrust, about megathrust systems generally, or about how communities prepare for threats like this? The most informed comment section is the one where the questions keep getting harder. That's the goal here. Stay curious, stay aware,